Today we're breaking down something every mechanic hears, but not everyone truly understands. 6.7 liter, 5.9 liter, 15 liter. What does it actually all mean? Is it horsepower? Is it torque? Is it physically how big the engine looks? Today we're going to explain engine displacement in a way you'll never forget, and we're going to calculate it step by step using a real engine you see every day, the Cummins ISB 6.7 liter. By the end of this video, you'll be able to explain displacement confidently, calculate it yourself, and understand why manufacturers choose certain bore and stroke dimensions. But again, what is engine displacement? It is the total volume of all the cylinders combined from bottom dead center to top dead center. In simple terms, it's how much air the engine can physically move per full piston sweep. And in diesel engines, air movement equals torque potential. There is an important distinction we need to make. Displacement measures volume, not necessarily power. You could have a small engine with a big turbo making huge horsepower, or a big engine making modest horsepower, but displacement always tells you one thing: how much air the engine can actually move naturally. Now let's imagine one cylinder as a drinking glass. The bore is the width of the glass, like this, and if you make the glass wider, it obviously is going to hold more. But if you make it taller, it's also going to hold more. That's the same idea inside an engine. But if you've watched any of my other videos, you've likely learned that diesels are torque machines. Unlike high RPM gas engines, diesels operate at lower RPM, rely on cylinder pressure for combustion, and move large volumes of air. That's why heavy-duty engines often have large displacement. The Cummins ISB 6.7 liter is common in Dodge Ram trucks, medium-duty trucks, school buses, and industrial equipment. But why 6.7 liters? Because that provides a nice balance of torque, packaging size, emissions control, durability, and displacement, which all together equal more low-end pulling ability. But how does that compare to, say, a 15-liter semi-truck engine? The 15-liter will be capable of producing a lot more torque, and it moves a massive air volume more than the 6.7-liter. However, displacement depends on only three factors: bore, stroke, and the number of cylinders. That's it. Not compression ratio, not turbo boost, not camshaft size, just simple geometry. So let's talk about what the bore is. It is simply the diameter of the cylinder. Pretend this cup once again is our cylinder, and this measurement across from wall to wall is the diameter. A larger bore equals more area, which equals more volume. Stroke, on the other hand, is the distance the piston travels from bottom dead center to top dead center. A longer stroke equals more volume. So if you have the cup a little bit higher, you're going to have a longer stroke and more volume. Cylinder count is pretty straightforward. More cylinders equals the total volume of each cylinder multiplied by the number of cylinders. Common configurations are 6, 8, and 10 cylinders, but there are other configurations as well. Now it's time for a little math. Here's the displacement formula. Displacement equals pi divided by 4 times bore squared times stroke times the number of cylinders. Now let's break down why pi over 4 is in there. The piston top is a circle. The area of a circle is pi r squared, where r equals the radius, which is half the diameter of the circle. So think distance from the middle of the circle to an outer edge of the circle. But engines measure bore as diameter, not radius. Since the radius equals bore divided by 2, when we plug that into the formula, it simplifies to pi divided by 4 times the bore squared. And that gives us the circular area of the piston. We then have to multiply that area by the stroke length to get the cylinder volume or displacement of one cylinder. We then multiply that volume by the number of cylinders overall in the engine to get the full engine displacement. Now let's do this with real numbers with the Cummins ISB 6.7 liter. We're going to start with some specifications. Of course, we have 6 cylinders. The bore is 107 millimeters, and the stroke is 124 millimeters. Now first off, we don't want to use millimeters to calculate this. We want to use centimeters. So let's convert from millimeters to centimeters by dividing the millimeters by 10, as there are 10 millimeters per centimeter. So for 107 millimeters, we get 10.7 centimeters, and for 124 millimeters, we end up with 12.4 centimeters. Now that we have the proper units, let's start with step 1, calculating bore squared. 10.7 centimeters times 10.7 centimeters equals 114.49 centimeters squared. Step 2, we need to multiply by pi over 4. 0.7854 times 114.49 centimeters squared equals 89.93 centimeters squared. That gives us the area of the piston. And now we need to calculate the volume of the whole cylinder by multiplying that area by the stroke length. So step number 3, multiply by the stroke. We've got 89.93 centimeters squared times the stroke length of 12.4 centimeters to end up with 1,115.1 centimeters cubed. Notice how multiplying the units changes them into cubic centimeters, which is correct and what we want and need for a volume calculation. This is the displacement of one single cylinder. To find total engine displacement, we then need to multiply by the total number of cylinders, which in this case is 6. So 1,115.1 cubic centimeters times 6 cylinders gives us 6,690.6 centimeters cubed. But it's called a 6.7 liter engine, right? Not a 6,690.6 centimeters cubed engine. Well, yes, and that's because we still need to convert those cubic centimeters into liters. 6,690.6 divided by 1,000 cubic centimeters per liter gives us 6.69 liters, which, when rounded up, gives us that even 6.7 liters. That's displacement. In North America, experienced technicians may talk cubic inches instead of liters, where 1 cubic inch equals 16.387 centimeters cubed. So to convert to cubic inches, we divide that 6,690.6 cubic centimeters by 16.387 inches per cubic centimeters. So for 6,690.6 cubic centimeters divided by 16.387 inches per cubic centimeter, we get 408 cubic inches around there. So the 6.7 liter Cummins is about 408 cubic inches. That might give better context if someone's comparing that to older 400 cubic inch gas engines. But now let's talk about bore versus stroke design and some of the philosophy behind that. Because here's where things get a little bit interesting. The ISB 6.7 has a 107 millimeter bore and 124 millimeter stroke. That means it's a long stroke engine. And long stroke engines make strong low end torque, have higher piston speeds, and favor diesel combustion characteristics. But you see short stroke engines, on the other hand, rev higher and make peak power at higher RPM. Diesels almost always lean towards this longer stroke design, and that's intentional. More leverage on the crankshaft equals more torque. But keep in mind, there are some things that displacement does not tell you. This is going to include things such as turbo size, fuel system capability, injector flow, emissions equipment, or simple horsepower rating. You can have two 6.7 liter engines making completely different horsepower numbers, because displacement is just the foundation and airflow management determines the rest. Now here's a quick what-if example to really help with understanding this concept. What if we could increase the stroke in our ISB 6.7 liter example by just 5 millimeters? The stroke would become 129 millimeters or 12.9 centimeters. That small change would noticeably increase displacement. The single cylinder displacement would be about 1,160 cubic centimeters. And if we multiply that by 6 cylinders, we're going to end up around 6,960 cubic centimeters, which, when converted into liters, would become a lot closer to a 7.0 liter as opposed to a 6.7 liter. So a small dimensional change can equal a really big, huge volume difference. That's why machining tolerances during rebuilds matter so much. Even deck height changes that are very small can affect the final displacement slightly. So now you know exactly what it means when someone says that engine moves 6.7 liters of air every full piston sweep cycle. Literally nobody will ever say it like that, but you would know if they did. However, you do know now how to calculate it, you know what affects it, and you know why manufacturers design it that way. But displacement is only one of the key components every diesel technician should know, so watch this video next to build on this knowledge and learn about diesel engine compression ratios.